This video is going to look at the answers and point values for AP practice problem G. This practice problem basically involves a parking lot, and they give you two functions. They talk about function that gives you the rate at which cars enter this parking lot, and then another function that gives the rate at which the cars leave the parking lot. All of the time is measured from 5 a.m., which is considered time zero, and the functions are both defined. I think they mentioned the one function where its table is differentiable. This thing's clearly differentiable. And that everything's valid between 0 and 12, which is basically from 5 a.m. to 5 p.m., so 0 to 12 hours. All right, and both of them are the rate function. So one thing to keep in mind, similar to the previous practice problem, is that this table isn't giving you the function values. It's basically giving the rate value. So it's the derivative of the cars function. So they don't really define the cars function, but they do define this cars entering function, cars rate at which they enter, and cars rate at which they leave function. This one's, like I said, clearly continuous. This thing's differentiable, so it's also continuous, but you don't have the in-between values. You can't really know exactly what the leave rate is at 3 because they didn't give you the ability to find that. All right, so with all that information, let's see if we can answer the questions. Well, part A, they want to know what is the rate of change of E of t. Now keep in mind, E of t is already a rate. It's being measured in cars per hour. It's how quickly cars are entering, per hour at any given time. They want for time 10, and they want us to indicate the units of measure. And since we have E of t as an analytic function, we basically just need to calculate what's the rate of change at a particular instant. That's what the derivative gives us. It gives us instantaneous rate of change. So I need the rate of change of E at 10, which is E prime of 10. Use a calculator to get that. You can just throw this in the calculator, go to the derivative, throw in the function, and then tell it that you want it at 10. And it should pump out 3.383. Now, what are the units? This way we have to be careful because they go, oh, the rate of change. That must be cars per hour. But realize it's the rate of change of the rate of change. So E of t is already cars per hour. So basically, this is the change in cars per hour per each hour. So if cars per hour are changing itself per hour, you're basically doing cars per hour, or better written as cars per hour squared. So those are the units of measure. In this problem, I think when I was looking at it, I was thinking, oh, they give you a point for each one of these, but they didn't. You basically needed the value and the units to get the point. So it's a little stinky because if you miss one, there goes the whole problem. But this has gotten out of a calculator, so I guess it's kind of fair to think, well, you can just punch a few buttons and hopefully understand the concept. All right, that gets us through A. Part B wants to know, well, how many cars actually entered the lot? Now remember, they gave you the rate of change of cars entering. They didn't give you the actual car, like accumulation function, how many cars are there at any given time. But we can use an integral to get this. They want to know how many cars entered the parking lot from 0 to 12. Basically, I want to take that entering function and integrate it. It will accumulate how many cars are in there at any given time. It also says give the answer to the nearest whole number. So you get a point for knowing that in order to change E of t, remember E of t is in cars per hour. If you integrate, it gets antiderivative. You just get cars as your unit. So if you integrate this 0 to 12, they literally want this as the work. So you get a point for saying to integrate this function. You could even just say integral of 0 to 12 of E of t dt if you really wanted to, because E of t is defined to be this function. As long as you say that, you get a point, but you need its value as well, and they want it to the nearest whole number. So if you throw this into a calculator, once again, to do this by hand would be extremely difficult, but it's calculator active because it's got a funky function here. So if you just throw this into the calculator, it'll pump out, so I think a little over 520, but set to the nearest whole, so it rounds to 520 cars. So basically, over those 12 hours, that rate of change function integrated tells you that 520 cars total have come in. Now they talk about the leaving function, which once again, we don't have an exact analytic form from, we just have the table. So they want us to approximate using a trapezoidal sum with 4 subintervals, indicated by the data in the table, because the table basically has 4 subintervals. They want us to be able to approximate, actually, correction, the table has, I think, 5 subintervals. Nope. Well, let's look. 1, 2, 3, 4. Sorry, I was right the first time. Shouldn't have corrected myself. Or tried to. So they want us to use the 4 subintervals from the table to evaluate this and tell us what it means. Well, you kind of get this problem. Integrating the entry function gives you the total number of cars that entered. Integrating the leaving function should give you the total number of cars that left from time 2 to time 12. And I said the reason I had to go back and check the interval because the other function starts at 0, but this one they don't give you the value at 0, so they just ask from 2 to 12 because they can't really go from 0 to 12 because they didn't give you a value for 0. So they want us, like I said, to get that trapezoidal sum, interpret what this means with the correct units, and approximate it with the correct units, and then the last part is to interpret the meaning of it. All right, so in order to get all these parts, once again, I drew a little sketch of what was happening. Here are all the function values, so the dots are the function values at each one of the interval spots that they gave me. This forms 4 intervals, which makes 4 trapezoids. Basically, if you just connect a straight line between all these points, you make all these right trapezoids. Now, the equation for the area of a trapezoid would be handy. A trapezoid is 1/2 base 1 plus base 2 quantity times the height. So these are on their sides. So you have to realize this is base 1, this is base 2, and this is the height of the trapezoid. Think of them, I can turn the paper. If you think of the trapezoid this way, basically these are the parallel sides and this is the height. So we have it turned the other way, but we can basically add each function value, the 15 to the 40, multiply it by this width, which is 3, and then cut it in half because that's part of the trapezoid formula. So you do that over and over again. So just showing it for the first one, I did the 15 plus the 40 times, those are the bases, times the height, times the 1/2. Put that all together, the area of, I called it T sub 1 for trapezoid 1, it's 82.5. You do this for all 4 of them and add them up. So basically there's a point for recognizing how to do the trapezoid, basically getting the trapezoidal areas, and then a point for adding them all up. So I think they did allow this to be grouped. If you basically got this, I believe they gave you both points, or at least if you showed the sum. So that 345.5 is the approximation of my area. Now the area is the same thing, well, since this is approximation, the area is approximating this integral, and so this gives us a number for what the integral means. Now that's what they ask us, not only to get the value of the integral, but what does it mean? What does the integral from 2 to 12 of the L of t dt, the leaving function, mean? Well, the leaving function was a leaving rate. If you integrate the leaving rate, you just get the total cars that left. So this is basically telling us on the interval from 2 to 12 how many cars left. Now, it's a decimal, so you could round it either way, I would guess. If they wanted you to round up, you go 346. But the way I saw it is, this is, in math, it's a model. It's close to the real value, but not quite exact, because clearly we can't have 0.5. Remember, it is an approximation. So I would think, according to this approximation, well, you didn't quite get the next car, so I rounded it down. But in this case, I think just getting this answer was good enough, because after this they wanted the interpretation. But I basically said it's about it all means about 345 cars left the parking lot between time is 2 and time is 12, which, since we started at 5 a.m., time is 2 is 7 a.m., and time 12 would be 5 p.m. This is 2 hours later and 12 hours later. All right. To be more specific, they do ask what this meant, so I would probably answer their question directly. They say, explain the meaning of this set of symbols. This set of symbols represents this quantity. I mean, this set of symbols means, this integral is just the amount of cars that left the parking lot total between these two times, which I said we calculated to be approximately 345, 346-ish. All right, and then the last part, they now break it up into 2 sections. So I think we're back talking about cars that are entering. Apparently when the cars enter, they're being charged a fee. So for time 0 to 6, so this would be the first 6 hours, basically from 5 a.m. to probably, it must be 1 p.m., right? Or sorry, 6, I can't add, 11 a.m. So from 5 a.m. to 11 a.m., they're charging them $5, and then I guess once it hits 11 a.m., they raise the rate, and then from 11 a.m. to 5 p.m., the next 6 hours, they charge them $8. So you would need to know how many cars entered in this section, how many cars entered in this section. It was basically redoing a problem we just did. And then multiply the number of cars times whatever the values are, because that's how much money they would get. So basically they want to know how much money did they end up collecting total for the parking lot between the hours of 0 and 12. So what they want you to know about integrals number 1 is we already integrated the whole thing, right? We know 520 cars entered. The problem is we don't know how many cars entered from 0 to 6 and then from 6 to 12. But we can break this up. We can basically do that problem. We can say, well, I'll integrate from 0 to 6, get that value, and then pick up from where I left off, integrate from 6 to 12, and get the next value. So basically, I broke up into those two pieces. How many cars entered from 0 to 6, basically, times 0 times 6, or 5 a.m. to 11 a.m. Well, this is the integral that would represent that. Now, you could write out the whole thing. This time I just put e at t dt and threw it into a calculator and got 210.141. So once again, it's a mathematical model, so it's close, but it's a little bit off because it gives us a fraction of a car. So it's roughly 210 cars. And they do want me to round to the nearest whole dollar, but I'm going to leave this I'm going to round at the end. So I'm going to keep the level of precision, I guess, or accuracy. It's one of those. Either way, this thing has a few decimal places. I'll keep it to not round it. Then I need to integrate from 6 to 12. Well, if I'm going to integrate from 6 to 12 of the same function, I can do the same thing through a calculator. So now it basically breaks up those 520 cars we have. We now know how many came in earlier and how many came in later. So it's about 210 and about 310, which adds up to about 520. So that sounds good. Basically, they gave some points for just setting up an integral with E of t gave you a point. And I think putting the correct limits here, knowing to break up into two different integrals, gave you another point. So now you go ahead and do the really easy pre-calculus part. Well, so that you know how many cars, how much money did they collect? Well, these cars were all charged $5. These cars were all charged $8, so you multiply. You get these money totals, you add up the money, and now they do want round to the nearest whole dollar. So now I've kept everything as close as I can, without over-rounding anything. I came out with $3,530.14. Round that to the nearest dollar, which is about $3,530. So this parking lot's making a good amount of money, right? So for those 12 hours it was operating, you got $3,530. All right, so another one of these table questions, and hopefully you see they asked the derivative, but most of it was about integrating because they gave you rates of change. So they tested integration in different ways: a standard integral, Riemann sum approximation with an interpretation, and then breaking up the integral. Once again, part B and part D are pretty similar, so they sort of tested the same concept twice. They went a little farther by making you do something with it. But like I said, they usually don't go overboard testing the same concept, but they did on this one. So once again, this one has a table and a function in it, where problem F, the one that preceded this, had just the table in it. So they, like I said, they like tables, analytic functions, and graphs. So they normally do some combination of them. This time they didn't put the graph in, but they definitely hit the analytic function in the table. All right, and I believe I went over all the point values, so you should know how you can get all 9 points on this, or if you did it and you could see where you went wrong, what points you might not have gotten. All right, that's AP Problem G. Obviously, following the alphabet. Up next, in the next video will be AP Practice Problem H. See you then.